After completing the viewing of this video and the accompanying spreadsheet, you should be able to compute the expected time for completing a project activity, account for variances and standard deviation in activity times, interpret a precedence table, construct a node diagram, and also identify the critical path and the possible project completion time. A project is nothing more than a set of related activities and their corresponding constraints, typically leading to a common goal or goals. So, said that way, everything in life becomes a project of sort. We look at a table format to identify the dependence of activities on each other. Sometimes we're going to do an activity till one is finished, and that determines the length of time it's going to take us to conceivably finish a project. Expected times refers to a weighted average of different times, such as optimistic times, pessimistic times, and what the industry experts think most likely times. There's a simple formula to do that, and we'll look at it in just a second. We can also apply statistics to measure the dispersion or variation of these times from each other. A node diagram is a graphical illustration of the sequence of activities. It is very interesting and very easy to do, and it really highlights where the critical path is. Where is the path that's going to determine, path along activities that is, that will determine how long the project will take. A Gantt chart is a graphical display that shows the different tasks lined up on a chart, sort of like a bar chart, and it states the beginning, end dates, dependencies, among other factors. We will look at these things individually in the next few slides. In this example, we will look at a lawn planting project. It could be for a commercial site or residential site. The blue area highlights what we call a precedence table. It identifies the various activities that we need to undertake to complete a successful lawn planting project, and we label each activity by a letter. We also note the precedence or the dependence on one activity over another. So steps A and B, or activities A and B, are the beginning of the project, and they really can go concurrently at the beginning, and they don't depend on anything prior to that. However, the rough grading of the terrain, activity C, depends on the completion of A. So A has to be finished, whatever length of time it takes, before we go on to the step C, and likewise the following steps. Now let's take a look at the completion time. If the gray area, there's three shades, where one lists the optimistic time, abbreviated A, to finish a certain activity. Most likely time, abbreviated M, also gives us what experts think is a most likely time to finish an activity, and pessimistic, meaning worst case scenario, abbreviated as B. So activity A, cut trees, depends on nothing before it, before we get started, has really a range of optimistic, most likely, and pessimistic. Let's look at step B, or activity B, remove trees. The most optimistic time, meaning it can be finished in 1 unit of time, that could be 1 day, 1 week, or 1 month. Most likely time, the experts say, is 3 periods, day, week, or month. And pessimistically speaking, it may take up to 5. Why? Weather could be a factor, other items could be a factor. So what is the expected time? The expected time is the weighted average of the optimistic, 4 times the likely, and pessimistic times. The reason we say 4 times the most likely is that we put a weight of 4 on the most likely time. That means we have the most confidence that that is the likely time or the expected time. The formula is very simple. Expected time equals A plus 4 times M plus B, and we divide that by 6 to find the weighted average. The expected time thus becomes 2 for activity A, 3 for activity B, and so on. And you see the result in the lower section of the screen, where we cleaned up the what seems like a complex spreadsheet into a precedence table with expected times right next to it. Before we move on to the next discussion, let's take a brief look at what we mean by variance and standard deviation. Variance is simply computed as G4 in this case, which is the pessimistic time, minus E4, which is the optimistic time, divided by 6 and then squared. That gives us an idea of the variance around the most likely time. The standard deviation is exactly that, and the standard deviation is typically the square root of the variance, and that tells us of how dispersed these values are around the mean. We will not discuss these things until a later lesson in the future. One of the best ways to analyze and understand a project and convey our thoughts on it is to go graphical. So in this section of the video, we're going to look at the precedence table, which shows the activity, the description, the precedence, and the expected time, and then draw circles representing these activities and their completion time. And you'll notice that we draw arrows to declare the dependence of one step over another. And by the time we go activity by activity, we notice that there are many paths that we can take from start to finish, which is step H. There are many paths we can take around this representation of the project, which we call a node diagram. And we can identify them by letter, and let's do them in this case one at a time. Path 1. Path 1, we can start obviously at the starting point. A2, that's A taken 2 units of time, C, F, and H. So A, C, F, and H is one path from beginning to finish, and the time it's going to take us is 10 units of time. Path 2 is A, C, E, G, and H, and the total time there is 16. And we similarly complete paths 3 and 4, and we find out that there are really no other plausible paths to finish the project except these. So what is the critical path? I highlighted the critical path in red color. Why? That signifies the longest time along dependent activities. So if we spend 16 units of time, let's say 16 weeks, we ensure that all the other paths have been completed. So the critical path becomes the fastest time we could possibly finish the project, unless we put more resources and shrink the time it takes certain key activities along the way. So we draw the node diagram, we identify the longest path, and that is the critical path, and that tells us how long it's going to take us to complete the project, satisfying all the constraints set in the precedence table. Now let's represent this project in a different visual interpretation. We call this a Gantt chart. A Gantt chart is nothing more than a bar chart displaying project tasks against a timeline, indicating start and end dates, duration, and dependencies. So in this case, we copied the precedence table and the expected times onto the screen, and then we highlighted cell by cell the duration. So let's take activity A. It's the start of the project, duration 2. Activity B has no precedence, so it starts at the same time, and its duration is 3. Activity C depends on the completion of A, so we move 2 time periods, and then we begin step C. And you'll see it noted in red, where the gray activity A or step A ends, that's when activity C begins. And likewise, D depends on B and A. However, B is longer than A, so activity D cannot begin till the longest of the A or B activities have been done. And if we continue the same sequence of thoughts and highlight the cells in the spreadsheet accordingly, and I like to use different color for each activity just to make it easy to follow, we will notice that the completion time is 16 weeks, almost identical to what the critical path method using the node diagram got us. So 16 weeks is the earliest that we can finish this project covering all activities. Before we leave this, let's look at one more consideration. What if we decided that we can finish step D, activity D, in 3 weeks instead of 4? Take a look at it. 3 weeks instead of 4. Would that make the project completion time any faster? The answer is no, because it is not on the critical path, and making it 3 weeks does not change activity E, which the following activities G and H depend on. So certain activities, visually inspecting them, you could tell that they're shrinking or they're crashing, as we say in project management. Finishing them in less time may not help. That really guides our decision on where to put our resources. We should not put any resources to finish activities that do not influence the faster completion time. So instead of spending money on activity B and ordering grass, maybe we ought to spend that kind of money on step G, start the planning and finish it in less than 5 weeks, or 5 periods. For every period we shave off step G and also step H, as you see, the project will be completed earlier and obviously or possibly for less money.